Chapter 9, API Gateway and Circuit Breakers. This chapter covers implementing edge services with Spring Cloud Gateway and Reactive Spring, configuring circuit breakers with Spring Cloud Circuit Breaker and Resilience 4J, defining rate limiters with Spring Cloud Gateway and Redis, managing distributed sessions with Spring Session Data Redis, routing application traffic with Kubernetes Ingress. In the previous chapter, you learned several aspects of building resilient, scalable, and cost-effective applications using the reactive paradigm. In this chapter, the Spring Reactive Stack will be the foundation for implementing an API gateway for the Polar Bookshop system. An API gateway is a common pattern in distributed architectures, like microservices, used to decouple the internal APIs from the clients. When establishing such an entry point to your system, you can also use it to handle cross-cutting concerns, such as security, monitoring, and resilience. This chapter will teach you how to use Spring Cloud Gateway to build an edge service application and implement an API gateway and some of those cross-cutting concerns. You'll improve the resilience of the system by configuring circuit breakers with Spring Cloud Circuit Breaker, defining rate limiters with Spring Data Redis Reactive, and using retries and timeouts just like you learned in the previous chapter. Next, I'll discuss how to design stateless applications. Some states will need to be saved for the applications to be useful. You have already used relational databases. This chapter will teach you how to store web session state using Spring Session Data Redis, a NoSQL in-memory data store. Finally, you'll see how to manage external access to the applications running in a Kubernetes cluster by relying on the Kubernetes Ingress API. Figure 9.1 shows what the Polar Bookshop system will look like after completing this chapter.
Figure 9.1. The architecture of the Polar Bookshop system after adding Edge Service and Redis.
Note: the source code for the examples in this chapter is available in the Chapter 09/09 Begin and Chapter 09/09 End folders containing the initial and final states of the project. See this link. Section 9.1, Edge Servers and Spring Cloud Gateway. Spring Cloud Gateway is a project built on top of Spring Webflux and Project Reactor to provide an API gateway and a central place to handle cross-cutting concerns like security, resilience, and monitoring. It's built for developers, and it's a good fit in Spring architectures and heterogeneous environments. An API gateway provides an entry point to your system. In distributed systems like microservices, that's a convenient way to decouple the clients from any changes to the internal services APIs. You're free to change how your system is decomposed into services and their APIs, relying on the fact that the gateway can translate from a more stable, client-friendly, public API to the internal one. Suppose you're in the process of moving from a monolith to microservices. In that case, an API gateway can be used as a monolith strangler and can wrap your legacy applications until they are migrated to the new architecture, keeping the process transparent to clients. In case of different client types, single-page applications, mobile applications, desktop applications, IoT devices, an API gateway gives you the option to provide a better crafted API to each of them depending on their needs, also called the back-end for front-end pattern. Sometimes a gateway can also implement the API composition pattern, letting you query and join data from different services before returning the result to a client, for example, using the new Spring for GraphQL project. Calls are forwarded to downstream services from the gateway according to specified routing rules, similar to a reverse proxy. This way, the client doesn't need to keep track of the different services involved in a transaction, simplifying the client's logic and reducing the number of calls it has to make. Since the API gateway is the entry point to your system, it can also be an excellent place to handle cross-cutting concerns like security, monitoring, and resilience. Edge servers are applications at the edge of a system that implement aspects like API gateways and cross-cutting concerns. You can configure circuit breakers to prevent cascading failures when invoking the services downstream. You can define retries and timeouts for all the calls to internal services. You can control the ingress traffic and enforce quota policies to limit the use of your system depending on some criteria, such as the membership level of your users, Basic, Premium, Pro. You can also implement authentication and authorization at the edge and pass tokens to downstream services, as you'll see in chapters 11 and 12. However, it's important to remember that an edge server adds complexity to the system. It's another component to build, deploy, and manage in production. It also adds a new network hop to the system, so the response time will increase. That's usually an insignificant cost, but you should keep it in mind. Since the edge server is the entry point to the system, it's at risk of becoming a single point of failure. As a basic mitigation strategy, you should deploy at least 2 replicas of an edge server following the same approach we discussed for configuration servers in Chapter 4. Spring Cloud Gateway greatly simplifies building edge services, focusing on simplicity and productivity. Furthermore, since it's based on a reactive stack, it can scale efficiently to handle the high workload naturally happening at the edge of a system. The following section will teach you how to set up an edge server with Spring Cloud Gateway. You'll learn about routes, predicates, and filters, which are the building blocks of the gateway. And you'll apply the retry and timeout patterns you learned in the previous chapter to the interactions between the gateway and the downstream services. Note: if you haven't followed along with the examples implemented in the previous chapters, you can refer to the repository accompanying the book and use the project in Chapter 09/09, begin as a starting point, this link. Section 9.1.1, Bootstrapping an Edge Server with Spring Cloud Gateway. The Polar Bookshop system needs an edge server to route traffic to the internal APIs and address several cross-cutting concerns. You can initialize our new Edge Service project from Spring Initializer, start.spring.io, store the result in a new Edge Service Git repository, and push it to GitHub. The parameters for the initialization are shown in Figure 9.2.
Figure 9.2. The parameters for initializing the Edge Service project.
Tip: in the Begin folder for this chapter, you'll find a curl command you can run in a terminal window. It downloads a zip file containing all the code you need to get started without going through the manual generation on the Spring Initializer website. The dependencies section of the auto-generated build.gradle file looks like this.
See this code?
These are the main dependencies. Spring Cloud Gateway, org.springframework.cloud Spring Cloud Starter Gateway, provides utilities to route requests to APIs and cross-cutting concerns like resilience, security, and monitoring. It's built on top of the Spring Reactive Stack. Spring Boot Test, org.springframework.boot Spring Boot Starter Test, provides several libraries and utilities for testing applications, including Spring Test, JUnit, AssertJ, and Mockito. It's automatically included in every Spring Boot project. At its core, Spring Cloud Gateway is a Spring Boot application. It provides all the convenient features we've been using in the previous chapters, such as auto-configuration, embedded servers, test utilities, externalized configuration, and so on. It's also built on the Spring Reactive Stack, so you can use the tools and patterns you learned in the previous chapter regarding Spring Webflux and Reactor. Let's start by configuring the embedded Netty server. First, rename the application.properties file generated by Spring Initializer, edge service/src/main/resources, to application.yml. Then open the file and configure the Netty server as you learned in the previous chapter.
Listing 9.1. Configuring Netty server and graceful shutdown.
The application is set up so you can move on and start exploring the features of Spring Cloud Gateway. Section 9.1.2, Defining Routes and Predicates. Spring Cloud Gateway provides 3 main building blocks. Route. This is identified by a unique ID, a collection of predicates for deciding whether to follow the route, a URI for forwarding the request if the predicates allow, and a collection of filters that are applied either before or after forwarding the request downstream. Predicate. This matches anything from the HTTP request including path, host, headers, query parameters, cookies, and body. Filter. This modifies an HTTP request or response before or after forwarding the request to the downstream service. Suppose a client sends a request to Spring Cloud Gateway. If the request matches a route through its predicates, the Gateway Handler mapping will send the request to the Gateway Web Handler, which in turn will run the request through a chain of filters. There are 2 filter chains. One chain contains the filters to be run before the request is sent to the downstream service. The other chain is run after sending the request downstream and before forwarding the response. You'll learn about the different types of filters in the next section. Figure 9.3 shows how the routing works in Spring Cloud Gateway.
Figure 9.3. Requests are matched against predicates, filtered and finally forwarded to the downstream service, which replies with a response that goes through another set of filters before being returned to the client.
In the Polar Bookshop system, we have built two applications with APIs that are meant to be accessible from the outside world, public APIs, Catalog Service and Order Service. We can use Edge Service to hide them behind an API gateway. For starters, we need to define the routes. A minimal route must be configured with a unique ID, a URI where the request should be forwarded, and at least one predicate. Open the application.yml file for the Edge Service project and configure two routes to Catalog Service and Order Service.
Listing 9.2. Configuring routes to downstream services.
Both the routes for Catalog Service and Order Service are matched based on a path predicate. All the incoming requests with a path starting with /books will be forwarded to Catalog Service. If the path starts with /orders, then Order Service will receive the request. The URIs are computed using the value from an environment variable, catalog_service_URL and order_service_URL. If they are not defined, the default value written after the first colon symbol will be used. It's an alternative approach compared to how we defined URLs in the previous chapter, based on custom properties. I wanted to show you both options. The project comes with many different predicates built in, which you can use in your route configuration to match against any aspect of an HTTP request, including cookie, header, host, method, path, query, and remote adder. You can also combine them to form AND conditionals. In the previous example, we used the path predicate. Refer to the official documentation for an extensive list of predicates available in Spring Cloud Gateway. See this link. Defining routes with the Java Kotlin DSL. Spring Cloud Gateway is a very flexible project that lets you configure routes the way that best suits your needs. Here you have configured routes in a property file, application.yml or application.properties. But there's also a DSL available for configuring routes programmatically in Java or Kotlin. Future versions of the project will also implement a feature to fetch the route configuration from a data source using Spring Data. How you use it is up to you. Putting routes in configuration properties gives you the chance to customize them easily depending on the environment and to update them at runtime without the need to rebuild and redeploy the application. For example, you would get those benefits when using Spring Cloud Config Server. On the other hand, the DSL for Java and Kotlin lets you define more complex routes. Configuration properties allow you to combine different predicates with an AND logical operator only. The DSL also enables you to use other logical operators like OR and NOT. Let's verify that it works as intended. We'll use Docker to run the downstream services and PostgreSQL, whereas we'll run Edge Service locally on the JVM to make it more efficient to work with, since we are actively implementing the application. First, we need both Catalog Service and Order Service up and running. From each project's root folder, run /gradle boot build image to package them as container images. Then start them via Docker Compose. Open a terminal window, navigate to the folder where your Docker Compose.yml file is located, Polar deployment/docker, and run the following command.
See this code?
Since both applications depend on PostgreSQL, Docker Compose will also run the PostgreSQL container. When the downstream services are all up and running, it's time to start Edge Service. From a terminal window, navigate to the project's root folder, Edge Service, and run the following command.
See this code?
The Edge Service application will start accepting requests on port 9000. For the final test, try executing operations on books and orders, but this time through the API gateway, that is, using port 9000 rather than the individual ports to which Catalog Service and Order Service are listening. They should return a 200 OK response.
See this code?
The result is the same as if you called Catalog Service and Order Service directly, but you only need to know one hostname and port this time. When you are done testing the application, stop its execution with Ctrl+C. Then terminate all the containers with Docker Compose.
See this code?
Under the hood, Edge Service uses Netty's HTTP client to forward requests to downstream services. As extensively discussed in the previous chapter, whenever an application calls an external service, it's essential to configure a timeout to make it resilient to inter-process communication failures. Spring Cloud Gateway provides dedicated properties to configure the HTTP client timeouts. Open the Edge Service application.yml file once again and define values for the connection timeout, the time limit for a connection to be established with the downstream service, and for the response timeout, the time limit for receiving a response.
Listing 9.3. Configuring timeouts for the Gateway HTTP client.
By default, the Netty HTTP client used by Spring Cloud Gateway is configured with an elastic connection pool to increase the number of concurrent connections dynamically as the workload increases. Depending on the number of requests your system receives simultaneously, you might want to switch to a fixed connection pool so you have more control over the number of connections. You can configure the Netty connection pool in Spring Cloud Gateway through the spring.cloud.gateway.http client.pool property group in the application.yml file.
Listing 9.4. Configuring the connection pool for the Gateway HTTP client.
You can refer to the official Reactor Netty documentation for more details about how the connection pool works, what configurations are available, and tips on what values to use based on specific scenarios, this link. In the next section, we'll start implementing something more interesting than merely forwarding requests. We'll look at the power of Spring Cloud Gateway filters. Section 9.1.3, Processing Requests and Responses Through Filters. Roots and predicates alone make the application act as a proxy, but it's filters that make Spring Cloud Gateway really powerful. Filters can run before forwarding incoming requests to a downstream application, pre-filters. They can be used for manipulating the request headers, applying rate limiting and circuit breaking, defining retries and timeouts for the proxied request, triggering an authentication flow with OAuth 2 and OpenID Connect. Other filters can apply to outgoing responses after they are received from the downstream application and before sending them back to the client. Post filters. They can be used for setting security headers, manipulating the response body to remove sensitive information. Spring Cloud Gateway comes bundled with many filters that you can use to perform different actions, including adding headers to a request, configuring a circuit breaker, saving the web session, retrying the request on failure, or activating a rate limiter. In the previous chapter, you learned how to use the retry pattern to improve application resilience. You'll now learn how to apply it as a default filter for all GET requests going through the routes defined in the gateway. Using the retry filter. You can define default filters in the application.yml file located under src/main/resources. One of the filters provided by Spring Cloud Gateway is the retry filter. The configuration is similar to what we did in Chapter 8. Let's define a maximum of 3 retry attempts for all GET requests whenever the error is in the 5xx range, server_error. We don't want to retry requests when the error is in the 4xx range. For example, if the result is a 404 response, it doesn't make sense to retry the request. We can also list the exceptions for which a retry should be attempted, such as I/O exception and timeout exception. By now, you know that you shouldn't keep retrying requests one after the other. You should use a backoff strategy instead. By default, the delay is computed using the formula first backoff multiplied by factor to the power of n. If you set the based on previous value parameter to true, the formula will be prev backoff multiplied by factor.
Listing 9.5. Applying the retry filter to all routes.
The retry pattern is useful when a downstream service is momentarily unavailable. But what if it stays down for more than a few instants? At that point, we could stop forwarding requests to it until we're sure that it's back. Continuing to send requests won't be beneficial for the caller or the callee. In that scenario, the circuit breaker pattern comes in handy. That's the topic of the next section.